Okay, so here's another introductory set. Again, these are cantilevers like we just did, except this one has a uniform load and this one has a triangular load. Again, to help us get started, I'm going to go ahead and tell you that the reaction force in the vertical direction here is basically the area of the curve, which is W naught over L. And then if you calculated the bending moment, it would be in this direction, and it would be W naught L squared over 2. And I think if you took time, you could easily verify that. But let's just say I've got those. Let's draw the shear force first and then the bending moment. So the first thing we want to do is, do I know the shear at my starting point here on the left side? I look up here and I do. What is it? It's W naught over L, and that's, what kind of shear is that? Positive or negative? Positive. What kind of shear do you think you have out here at the free end? It's not a point load there. So I think it's going to be, what does it look like to you? It looks like it's going to be 0. Let's see if we can make that happen. So to check that out and also to get the shape, let's go back to our original relationships. The change in shear is the area under the load curve. All right, so this is a nice continuous section. So what is the area under this part of the load curve? Well, it's a rectangle. Rectangle area is base times height. So that would be L times W naught. What kind of load is that? Positive or negative? It's a negative load. So that means I'm going to start at W naught over L, and I'm going to subtract W naught over L. And what do you know? I get 0. The slope of the shear diagram is equal to the value of the loading everywhere. Well, my loading is constant, so I'm going to have a constant slope. Has a value of W naught, and is it positive or negative? It's negative. So here's a negative slope between those 2 points that's constant. In fact, again, if you did the slope, you would get 1 to minus W naught is the slope. So there's your shear diagram. Okay? Let's do the moment. What's the starting bending moment at the left side? What kind of bending moment is this? Positive or negative? Negative. That's negative. So I'm going to start at a negative value of W naught L squared over 2. What's the bending moment at this free end without an applied moment? 0. So let's see if I can connect those dots. Well, I know that the change in moment between any 2 points is the area under the shear diagram. So my shear diagram's really continuous over the whole segment. So what's the area of that diagram? Well, it's a rectangle. I mean, it's a triangle, right? So 1/2 base L times height W naught L. That's W naught L squared over 2. And that's a positive area. So if you have negative W naught L squared over 2 plus W naught L squared over 2, you get 0. Yeah. So far, so good. What's the shape of the curve in here? Well, we know that the slope of the moment diagram is equal to the value of the shear. So let's look at the very beginning here. What's the slope of the moment diagram right there? Would be equal to the value of the shear. And what's the value of the shear? W naught. Is it positive or negative? Positive. So I'm going to draw a positive slope, and I'm even going to emphasize it by saying it's W naught to 1. Now, as I move from the left side to the right side, you can see my shear value changes, right? And what does it ultimately end up here to be? 0. What's the value of 0 slope? It's a horizontal line. Right? So all I have to do now is connect the curve that matches this slope and that slope. So I have a constant to linear, so this would be a quadratic curve. It doesn't really matter what it looks like. I just want you to draw the shape. Your curve will not accurately predict the value of the moment everywhere along the beam, but it will accurately predict what? The maximum value and where it's located. And that's all we really care about from these diagrams. This tells us that the maximum moment is at the cantilever, and it's negative L squared over 2. And then it decreases to no moment at the end. If you're really interested in the moment, say right here, what is the moment? What would you do? You'd have to come up here and find the area under this part of the curve, right? This trapezoidal area, and add that to this thing, and you would get that value. So you could do it if you needed it. You don't have to go back and write the equation if you don't want. We can still use our relationships. So constant load, when you integrate it, you get a linear shear. You integrate it, you get quadratic moment. All right, let's do this guy. So again, I'll go ahead and calculate and tell you that the value of that reaction is going to be W naught L over 2, and that the moment will be W naught L squared over 3. And if that really bothers you right now, just go ahead and solve for these reactions with a free body diagram of the structure, and you'll be okay. I did just want to quickly show you that the resultant force of that is W naught L over 2. So summing forces, that's how I get that. And then the distance from the wall or the support to here would be 2L over 3. You multiply those together, that's how I got that. Without going through all the formal equations of equilibrium, I just kind of show you that. All right, so let's apply our relationships and do shear and moment. So what is the shear at our starting point here? It is W naught L over 2. Is it positive or negative? Positive. What's the shear at this free end? 0. The change in shear between these 2 points should be the area in the load curve. What's the area under the load curve between those 2 points? What's the area of a triangle? 1/2 base L times height W. So that's W naught L over 2. Is this positive load or negative load? Negative. So WL over 2 minus WL over 2, 0. What's the shape of the curve? What's given by the load? So starting here, what is the load at the beginning? 0. So I got a 0 slope. And then the load increases to a maximum slope at the end. Is that a positive slope or a negative? A positive load or a negative load? Negative. So that means I have a big negative slope. So all I have to do is draw a parabolic curve or a quadratic curve that kind of fits those things. So I'll do my best. You get something that looks like that. Now you'll start to see the first of few serious drawbacks to this graphical technique. So let's draw the moment diagram. So do I know the moment at my starting point? Sure, it's W naught L squared over 3. Is that a positive bending moment or a negative bending moment? negative. So I will write here negative WL squared over 3. What's the moment at the end? 0. Let's see if I can make those two things match. So I know the change in moment is the area in the shear diagram. I don't know the area of a parabolic section off the top of my head, do I? Well, I do, but you probably don't. It just so happens that the area of this parabolic section is 2/3 base times height. And what makes it a parabolic section is one end has a 0 slope. So let's just say you knew that. So what's the area of this curve? 2/3 base L times height WL over 2. If you calculate that, you get positive WL squared over 3. So you add it to that, you do get 0. Yay! But you can see if this curve was something more complicated, you'd have to know the area underneath it. And if it's not some kind of nice rectangular thing that you know right off the top of your head, you're going to have some issues. You might even have to write the equation for the shear and integrate that. Well, then you're back to just writing equations again. So drawing shear force and bending moment diagrams is really good for point loads, for distributed loads that are constant. When you start getting to triangular loads, it gets a little problematic. I'm going to try to not start you off on these for a while. We'll move into those a little more slowly. That's my attempt anyway. So let's see if we can finish this part of the problem up. So the change in moment we've already checked. So what's the slope of the moment? Well, it's given by the shear. So look up here, starting here at the beginning, what is the shear at the left side? It's positive. So I'll just kind of sketch in what I think is a big positive slope. And it decreases to 0. That means I'd have a 0 slope here. So if you sketch this in, it would look something like that. Linear, quadratic, cubic. Ultimately, the question is, where's the maximum moment? It's at the cantilever, and you already found it. What's the maximum shear? It's at the cantilever, and you've already found it. Any questions about that? I got just enough time to do a couple more.